Hi everyone, I'm Kostadina, and in this section we're going to speak about neural networks. The biological motivation of neural networks comes from the human brain, where the basic computational unit is a neuron. The human brain contains around 86 billions of neurons, and these neurons are connected with synapses. In this image, you can see a drawing of a biological neuron. Neurons receive an input signal through the dendrites that process on the cell body. Then the axon carries the output of the neuron to its axon terminals that connect the dendrites of the other neurons using the synapses. A computational model of a neuron could look like the image on the right, but keep in mind that these analogies are quite loose. Here we have a cell body and an input x0 coming from another neuron through the axon. And this neuron is connected through the synapse, and every synapse is assigned to a weight w. So the axon carries the x0, it interacts with the synapse, and then the weight w0 is multiplied with the input x0 and flow into the cell body. That happens for multiple neurons, so we have a lot of inputs of w times x flowing into the cell body. The cell body performs a sum of these input dot products and adds a bias, and then passes this through an activation function to compute the output of this action and pass it to the next neuron. This can be interpreted as the rate that each neuron is firing for that particular input. There is an entire set of nonlinearities that we can choose to use. Some highly used activation functions are the sigmoid, that gives a number between 0 and 1, the tanh, that gives a number around -1 and 1, then the ReLU, or rectified linear unit, that gives x values when x is positive and 0 when x is negative, and finally the leaky ReLU, that is just a variant of normal ReLU. So these activation functions are used to introduce nonlinearities to the model. But why nonlinearities? In this case, where we have two classes, the red and the green, we can see that they can be easily separated with just a straight line. But what about this case on the right? It is clear that a linear function would not be sufficient to separate this data distribution. And that is why we use nonlinearities, as most of the problems in the world are not linear. Now let's see how a typical neural network looks like. First, we have the input layer. Then this input is connected with every node of the hidden layer, and then again with the output layer. And we call these layers fully connected layers. And the more hidden layers we add to the neural network, the deeper it gets. Now, when it comes to classification, we have some input features, and the output neurons are the number of target classes. So in this case, we have a three-dimensional input, and the output is the score for the two classes. But how does a machine learn? Let's say we have an input image and a set of output classes like cars, trains, and bikes. First, we have some input features that could be human-designed or directly take the pixels. These features could be the number of circles, the biggest shape, or the number of dark pixels, and are transformed into a vector and are fed into the neural network as a weighted input. So we arrange the neurons of the neural network in layers, and we connect all features to the input layer and then all outputs of the previous layer with all inputs of the text of the next layer, and in every connection we have weights. And then our final outputs are connected to an output class, and the highest value, 0.9, is the one that finally fires, and then we know that this is a train. This whole procedure is called forward pass, or forward propagation. Now, during training, we first initialize the weights of the neural network, and we tell it what should recognize. So in this case, for this specific image input, let's say we have assigned that it should recognize the trains using the output vector 0, 1, 0. And this is our desired label. Let's say that after some training, the output is 0.1, 0.9, and 0. So we compute the error between this predicted value and the actual label, that is 0, 1, 0. And according to that, we fix the parameters, which are the weights, and adjust them so that the error becomes even smaller. The learning algorithm behind this is called gradient descent, and it is based on the learning principle expectation maximization. The idea of expectation maximization is that we have a neural network, we test some input-output examples available on the training set, we run the neural network on these examples, we compute the error, and based on this error, we adjust the weight parameters, and we repeat that process to minimize that error. Let's see now gradient descent. On the x-axis, we have the weights, and on the y-axis, we have the loss function, or the error, that depends on these weights. And we don't know how that function looks like, but let's say that it is a convex function like the red one. And we want to find the place where the error is minimum. So we initialize the weights, and we compute the error that is on the upper left, the yellow cross. Keep in mind that we don't know the red function at all. Now, to adjust the weights and minimize the error, we calculate the gradients, which are basically the slope that show us the correct way to follow. And we repeat this process until we find a local minima, which is the winner. In general, the expectation maximization principle is an iterative method that estimates the maximum likelihood of parameters in statistical models. In the previous case, it was the error of the neural network, and then repetitively alternates between the expectation and maximization. So we have the expectation step where we update the parameters, and then we have the hypothesis where we update the hypothesis, the maximization step. So we re-estimate the parameters to maximize the expected log likelihood found in the expectation step. That was all for this session. Thank you very much.